guess it's a long title. And my travel from Berkeley was a little bit longer than described. I had a postdoc in 2 places. In any case, I indeed will give you some sign conditions for injectivity. So this is, sometimes people ask, injectivity, blah, 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 where is the functor? No, I really mean injectivity if you have a function from a set to another set. Do you have 2 points that map to the same point? And the motivation is I'm interested in questions from real algebraic geometry, namely where and when do I know if I have a system of polynomials if I'll have at most, let's say, 1 positive real steady state solution, sorry. But on the chemical reaction network side, I'm interested in the question, when does a chemical reaction network admit at most 1 positive real steady state? Okay, so I'll define all of these things as I come to it. Before I start, I want to say that the theorem that I'm going to present about the sign conditions is joint with many co-authors, Stefan Müller, Elisenda Filiu, Georg Regensberger, Carsten Conradi, and Alicia Dickenstein, who's here in the audience. So I think all of the speakers start by saying that they were influenced by Frank in some way about whether or not to give slides or not. So I'm giving a hybrid talk in which the first half will be on the whiteboard, and then I'll be giving 4 slides at the end. So here's my outline.
Could you get the light on?
Yeah, I can.
Yes. For this.
Here, that.
Thank you, Frank.
Let me help you. Oops.
It's okay, we can erase.
Okay.
Thank you.
I'll clean it off for you, actually.
So the first part of my talk, I'll give the motivation, and in particular, I'll tell you what are chemical reaction networks and why we're interested in steady states. So steady states of chemical reaction networks. In part 2, I'll give you the main result. That's, as I was describing, sign conditions for injectivity. Okay, so part 2 is a theorem, sign conditions for injectivity. Part 3 is the connection to real algebraic geometry, and in particular, I want to tell you what is the connection to Descartes' rule of signs and why we view it, our result, as in part a partial multivariate generalization of Descartes' rule of signs. Okay, so connection to Descartes' rule of signs. And then in part 4, I have the 4 slides that I promised on my computer, and I want to pose some questions since all of you are experts in solving polynomial systems. I want to put out some challenges that I hope some of you can help me solve. Okay, so some questions. Okay, so let's start. So normally I give an example coming from chemistry, but recently I think in the news there's been a lot of questions about disease and Ebola and modeling the effects and how it will continue to spread and so on. So I wanted to give an example not of Ebola but of the flu. Okay, so let's say example, a model of the flu. And in particular, let's start with what's called an SIR model. So who in the audience has heard these words SIR before? Okay, good. So some of you and some of you have not. Okay. So depending, I guess, what department you're in, sometimes you go to a talk and maybe every month somebody says the word SIR. And in my experience, it just depends on what department you're in. I guess in my current experience, I hear the word SIR every other week or so. I go to a talk of this form. And SIR stands for 3 words. S is for susceptible. Okay. I is for infected. Okay. So infected with the flu in this case. And R is for recovered. And so this, in general, the SIR model was first presented in 1927, but I want to give just a modified version that's a bit more realistic for the flu. Okay, so let's just say modified. So if you study epidemiology or anything, this is the first thing you studied at the very beginning. So let's write down some things that happen when the flu happens. So let's say that I arrive here, I have the flu, and you want to know, are you also going to get the flu? So let's write down some things that could happen. So if I have a susceptible person, that's you, an infected person, that's me, then let's say that you and I had lunch together and maybe we shook hands, and there's some probability that now I have transmitted the disease to you, and it also depends on whether you go wash your hands or not, right? So there's some probability where we will turn into two people that are infected. Okay? So this is people getting sick. Getting sick. Actually, so something that was to come is way down here. I want to write S goes to R. This is me. I got the flu shot, so I don't have the flu shot. Okay. And so maybe we're imagining all of you, right? There's some probability that you guys are getting a little bit nervous and you are all going to go and get a flu shot. So maybe a lot of you guys will turn into recovered people soon. Okay, and then let's write down some other things that can happen. If you're infected, then you eventually hopefully become recovered. Okay, so this is recovery. Okay. And let's say maybe some of you decide to go home, right? Okay, sorry? Is that, yeah, so usually this is people who are dying, but I decided to make this a bit more friendly, and so some of you are going home and not staying at Simon's for their Christmas semester. Okay, go home. Okay. Okay, but maybe you got sick and you went home, but you were supposed to give a talk, and so you send somebody else to come give your talk for you, and then those are people who are arriving. Let's say 0 goes to S, and 0 goes to R. But let's say if you have the flu, you will stay home. You won't come to give your talk. Okay, so these are arrivals. Okay. Okay, so now I've written down so by some depiction of arrows, some things that can happen, right, under this simple flu model. And what I have described is that each arrow only happens with certain probabilities, right? If I assign to each of these what I call reactions some rate, then that will describe how likely these things will happen. Okay, so I want to call this kappa 1, kappa 2, kappa 3, kappa 4, kappa 5, kappa 6, kappa 7, and kappa 8. Okay? And so, for example, if all of you guys are washing your hands on kappa 1, you should think of it as a very small but positive number. Okay? Because you're not going to get infected compared to maybe people getting the flu shot. Okay? And so what people, when they first wrote down the SIR model, is to write down in a deterministic setting what are the dynamics that arise from this? How many people will be susceptible, infected, and recovered, and how this changes in time? And so this is what people write down. Okay? So we have differential equations for each of the three. So of course you could do a stochastic or discrete version of these systems, but as long as under certain reasonable hypotheses, you can think of this as a deterministic continuous setting, and that's what we'll do today. Okay. So according to the law of mass action, this says that the number of times that two susceptible and infectious person becomes two infectious people is proportional to how many susceptible people there are and how many infected people there are. Okay, so in other words, the rate at which the number of susceptible people will change, okay, coming from this one reaction, is proportional to the product. So this is what is described by the law of mass action. It says that each, let me say in parentheses, reaction rate is proportional to the product of reactants. So if this was actually chemistry, then S and I would be actually what we would call chemical species. They're mixing together in some large vat, and they are reacting to become 2I. But here you should think there is this big auditorium room, and maybe we always mix together and have lunch together, and we shake hands and whatever. And the probability that these things will happen is proportional to how many infected people there are and how many susceptible people there are. Okay? So here I would write for this reaction, which takes place at rate kappa 1, the number of susceptible people will decrease because they became infected. So I would write this as minus kappa 1 times S times I. Okay, so here's my monomial S times I times a constant kappa 1. And then to write down all the rest of the differential equations, I just go through all of these reactions and write them down as a sum over all of these possible arrows. Okay. So for example, for S, the first reaction I already wrote down. The second one does not affect S. But then I have this third one where people go home. Okay, so I think I write minus kappa 3 S. And then at the end, there's the flu shot people. So this becomes minus kappa S times R, times S.
Plus kappa 6.
Kappa 6, yes.
No.
Kappa 8.
And then there's a plus
There's a
kappa
plus.
six.
Yes, and a plus kappa 6. Yep, plus kappa 6, because some people are arriving who are susceptible. And in particular, you can see I sort of made this example a little bit contrived in order so that there's actually positive real solutions, right? Because normally just everybody will eventually become sick, and then that's the end of the story. But now I'm assuming that there are some arrivals, so new people are coming in who are not been sick yet. Okay, so now let me just write down the rest for I and for R. So kappa 1 S times I minus kappa 2 I minus kappa 4 I. Okay, and kappa 2 I minus kappa 5 R plus kappa 7 plus a kappa 8 S. Okay. And this model is only valid if the number of people is kept constant. But maybe in this setting, right, the number of people here at Simon's is somewhat constant, so it would be okay.
People arrive sometime.
I was well, okay. So you could add it in. I don't think it affects much, but I didn't actually work it out. But maybe I was just thinking that people, if you're sick, maybe you would not show up, or I would hope that you would not show up. Okay. Okay. So you might start with this system of equations, and you might ask, okay, now I have a continuous dynamical system, and you might ask many questions. And there are many questions that you could ask, and I'm only going to focus on steady states. But if you're interested in other questions, for example, is the flu going to die out? Is the flu going to, or is everyone going to get the flu? That's an interesting question, which I will not talk about. You could ask the question, if I had solutions to this, so I have a trajectory of the form S, I, R. You could ask, from those solutions, can I actually recover all of these parameters? Right here are 8 parameters, but I have a solution set. Can I, the trajectories, can I recover these 8 parameters? If you're interested in this question, you should wait for Nikki's talk. She will tell you about these answers. Okay. You could ask questions about the understanding when there are certain numbers of steady states. So I might ask, can you decompose, give the semi-algebraic decomposition of the 8-dimensional parameter space based on how many steady states there are? Let's say, in this case, it happens to be 0 or 1, so it's a little bit silly. But in general, you might have some large number of steady states. And then maybe Talgata will be interested in solving this problem for me, for example. Okay, so there are very many interesting questions. But I want to focus today on the question of, okay, when are there less than or equal to 1 positive steady state? And since I haven't defined it, I should say definition. A steady state, okay, of this system of differential equations, okay, is some, let's say, S star, I star, R star, okay, at which the differential equations, the ODEs, are equal to 0. And in particular, since I'm looking at a network from biology, I'm interested in non-negative real solutions. Okay, R greater than or equal to 0 to the third. Okay. And if I wanted a positive steady state, which I actually do for this talk, I want to restrict to the strictly positive entries. Okay, so I could say a positive steady state is when I disallow when any of the coordinates is equal to 0. So you see what I'm doing, right? I took this system of 3 polynomial equations. I'm setting all 3 equal to 0, and then I'm asking how many solutions do I have, right? And how does this question depend on the kappas? So who sees how you can easily solve this system? It's very easy, right? It's almost linear except for one degree 2 term, right? But okay, so what should you do? What can you see but an easy trick?
Eliminate the degree 2 term.
Yeah, you can eliminate, right? But and there's something even easier here. The I cancels out, right? Yeah, you can divide the second term by I, so now it's linear, and then everything is good to go. So that's how you can see that there's only 0 or 1 solutions. Okay. Okay. But of course, we'd like to have theorems, right? We don't want to just have to try to do everything by hand or or to just blindly throw things into computer algebra. Okay, so that's what we will talk about today. Okay, let's see. Okay, so 3 lines of research. So what I did here was give you an example. This is a network, right? This consists of a bunch of reactions, arrows. Using the law of mass action, I write down a system of polynomial equations, and I'm interested in setting them equal to 0. Okay? So people who have studied this from the chemical reaction network point of view have used this special structure to get some nice theorems about trying to answer questions about the number of steady states. So broadly speaking, there are 3 areas of research that have developed, and the first is called deficiency theory. This began in the 1970s, and I guess has continued somewhat since then. And a basic idea, this is not the focus of my talk, but the basic idea is that you can compute a number, an invariant coming from the network very easily. And from this invariant, you can easily, sometimes, determine that there's no more than one steady state, and in fact, there's always a unique positive steady state. Okay? So if I were to give you a different example, which is completely contrived, I plus R plus S. If I looked at this network here, what deficiency theory would tell me to do is to compute something called the deficiency. Okay? And I do this by computing the number of vertices. Here it's 3. Okay. The number of components, that's equal to 1. Okay. And then I compute the dimension of the span of the 3 corresponding reaction vectors. Okay. So here it's 2R minus I minus S. And then I have R plus S minus I plus S. Okay. And then the third vector is just a sum of the other 2, but let's just write it to be clear. 2R minus R minus plus S. Okay. So if I look at the span of these 3 vectors, it's a 2-dimensional space. And what deficiency theory says in this case is that I subtract 1 plus 2 from 3. Okay. The deficiency is 3 minus 1 minus 2. I get 0. Okay. This is supposed to be a delta. And according to deficiency theory, since the deficiency is actually 0, then this system, if I wrote down the corresponding ODEs, would always have a unique positive steady state. Okay. So according to deficiency theory, in particular this deficiency 0 theorem, there's always a unique positive steady state. Or in other words, if I wrote down the system of equations, then regardless of what choice of parameters I picked, okay, so I could put, there are 3 parameters here, kappa 1, kappa 2, and kappa 3. The resulting system would always have a unique positive steady state, a unique positive real solution, okay, regardless of what kappas I picked. So there's a whole line of research in this area. The 2 areas, the other 2 topics, the other 2 lines of research I do want to talk a little bit about. And the third is the main focus, which is injectivity. Okay. So this is where our theorem fits in. And the second line I want to mention, which I'll say again later, okay, is the question of, well, going back to, I think maybe JM asked this question, what happens if I also included the reaction where people who have the flu are actually arriving? Could I have inferred from this computation the fact that if I added something else, maybe I would still have the same kind of result? Okay? So I think of this as lifting steady states from small to large networks. From small to larger networks. Okay. And I'll say a little bit about this when I do my 4 slides at the end, and Alicia will say more later this afternoon.
Is there more content to that deficiency theory? Like, is the steady state stable?
It's known to be locally stable, and the open conjecture, which is one of my main research focuses, is asking the question about global stability. Because there's a Lyapunov function and everything, but the issue is near the boundary when some of the coordinates are close to 0. Could it actually be the case that they go off to the boundary, they go off to infinity, or whatever? Yeah. And I'll show some pictures related to that near the end of my talk. Yeah, there's much more than I've described here. But from the point of view of just counting steady states, just counting positive real solutions, it just guarantees a unique such solution. Okay, so let me spend the rest of my board talk about injectivity, and then I will talk about part 2 and other open questions. Okay, so we're going to a slightly more general setting than the ODE system that I wrote down here, and I just want to think of any system of polynomials that has this sort of parameterized family point of view. Okay, so I want to consider polynomial maps parameterized by some kappa, okay, going from a positive orthot to all of Rn. Okay, and so one special case you want to think of is these mass action ODEs that I've described here. Okay. So the setup is a restricted polynomial map, because I want to restrict my attention to the positive orthot because I want to ask about positive real solutions and not all solutions in general. Okay. Let's say given by f kappa comma I of x is equal to some polynomial system. The coefficients are aij, but I want to be able to scale them by some kappas. So let's multiply it by kappa j, kappa ij, I believe. Let me double check this. Okay, x times x1 to the bj1, xn to the bjn. Okay. Sum from j equals 1 to r for I equals 1 up to n. Okay, so do I want a kappa ij or do I want a kappa j? Yeah. Okay. Okay, and then so how many do I have? So I have n equations, okay? And I can summarize the information coming from the exponents and coming from the coefficients. Okay. So for some matrix A, which is a real n by r matrix, okay, B is r by n, okay. And the kappa has 1 is a sum strictly positive sum over all of the possible monomial coordinates. Okay. And the example you can think in your head, at least for my application, is when these f sub kappas are those 3 differential equations there, okay, or 3 just polynomials. Erasing. So the first thing I want to mention is that in the setting of these ODE systems, there's often some conservation relations. So one thing I'd mentioned is maybe you want to think of the population as being constant. And sometimes encoded in these differential equations, there's actually some conservation relations. So in general, yes?
R is the degree of the monomials?
No, R is the number of terms, the number of monomials. These degrees could be arbitrary. Here's the monomial, and here are the coefficients in front of the monomial.
And then B are all the collection of exponents?
Yeah, B's are the encode all of the exponents in the monomials, and A encodes the coefficients here. But I want to scale them by some kappas. That's what my theorem will want to say something about. For all kappas, how many solutions do I have?
B's in R, then it's not really a polynomial map.
Sorry? Oh yeah. So that's what the title said. Generalized polynomials. Our theorem works in that setting, so I just said R. Yeah.
Many different terms for those. But
Yeah. There are many terms like sinomials and things like that, right? Yeah. Okay. So maybe in our paper we call them generalized polynomial maps. Yeah. Okay. So note, generally, conservation relations constrain trajectories of the solution, the ODE system. Okay, so if I had some dx dt as some f kappa of x. Okay, so I don't have an example like that. There's actually no conservation relations in this case, but in general, a picture typically looks like this. That the differential equations actually live in some lower dimensional subspace. Okay, so here, if you go back here and I look at these coefficients aij, okay. If I look at the corresponding column vectors, okay, those will constrain the space in which this map lives. Okay, so in general, this image will be a lower dimensional space, and so I'm interested in translations of this subspace. Okay, and my solutions will be confined to those. Okay, so this will be solution to the ODEs. Okay, will be in a translation of this subspace S. And in general, this might happen because maybe the systems are constrained in such a way that maybe the total amount of people infected and susceptible and resistant are actually constrained to be summing up to something, right? Maybe the number of people that are allowed at this conference are always some fixed number, okay? And sometimes it's reflected in the ODEs. 312. So if every seat was exactly full, then this would be what it was, okay? Okay, good. So the point, maybe if I use another color, it'll be a bit more clear, is that I'm interested in the set of steady states, which depends on kappa, but I want to count them relative to some specific translation of S. Okay? So I want to count within the set P, which is a translation of S plus some initial point, okay, intersected with the non-negative orthant. Okay. I want to count the number of steady states in here. Okay, so count steady states here. So this is the picture that I have in general, but not in this specific example. So the question of injectivity, which is the theorem I want to tell you about, starts from the basic premise, a very, very basic idea, which is that, well, if I want to ask, when I restrict to the set P, and I want to know, are there two or more points that both map to this point 0 under the map set of ODEs? Well, a basic condition for this to be true is if the map is injective to begin with, right? Because you can't have two things mapping to 0 unless there are two things mapping to the same point to begin with. So I'll write that as the basic observation. Sufficient condition for precluding multiple steady states. Is if the ODEs, the map of ODEs restricted to P, which goes from P to the subspace S, right? Because this is where my ODEs live, in the subspace S, okay? Is an injective function. Is injective for all P and for all kappas. So again, this is a very basic idea, right? I want to say, well, when is it that for any choice of my rate constants, okay, I never have two or more points within some invariant set P that go to 0? Well, a basic condition is if the map is always injective. Okay, and so what our injectivity theorem, which I'll now write down, says is we can check this condition using sign vectors.
Image is still a Korean, right?
Sorry?
Yes.
The ODEs live in S, no?
That's okay.
Okay. Oh, you mean in general? In general, yeah, in general, yeah, okay, but in the setting of mass action, that will be fine, yeah. Because you're asking about the reaction vectors. Yeah, I'm a little, in the setting I'm interested in, this is okay. Okay, so let's do some notation. Okay, so I just want to give notation for a sign vector. So if I have a vector x, so I will call this the sign vector, sigma of x. And just as an example, let's say minus 3 to 0. This sign vector is minus plus 0. It just records for each coordinate whether it's positive, negative, or 0. So here's our theorem. Our theorem characterizes exactly when this sufficient condition happens, and it gives 4 equivalent conditions for this. So the following are equivalent. 1. This exact condition happens. Okay. So for all p and for all kappa, this restricted map, f kappa restricted to p, is injective. Okay, so this is why we're interested. We want to find some equivalent conditions for checking this condition here. Okay, because let's back up. What is this asking? This is asking, I have a system of polynomials, and I want to ask for every parameter, so every single member of this family of polynomial systems, do I have at most one solution? So part 2, this one is easier to check. It says for all kappa and for all x in Rn plus, the Jacobian matrix Jacobian of f sub kappa of x is itself injective on S. So this is asking different questions, asking whether the Jacobian matrix is injective on this subspace S.
On S equals what there?
The image of A. This is what I'm defining as S. The image of this matrix A. Okay. Because before so the previous one is asking about all sets P. Now I'm asking about injectivity on a subspace F. 3. So if I wanted to compute whether the Jacobian is injective, then I just need to look at the determinant of this matrix. And so part 3 says, okay, now let's look at the terms in the Jacobian, in the determinant of the Jacobian. So I can write out what they are. So for all, I take subsets of n and subsets of r, okay, of size equal to the rank of A. Because remember, I'm in a lower dimensional space that's equal to the rank of A, size dimension equal to rank of A. I look at some determinants. So I look at the corresponding subdeterminant of A, defined by the rows I and the rows J. Okay. And I also look at the determinant of the corresponding entries of B. Okay, remember A is the coefficient matrix, B is the exponent matrix. I look at the corresponding determinants, and I want to say, to make sure that they're not of opposite sign. Okay, so in other words, I want to ask that the product is either 0 or has the same sign as all other non-zero entries. Non-zero such products. So either anytime this matrix, anytime the two determinants are not the same, they should either always be plus minus, or they should always be plus plus, or minus minus. Sorry, they should either always be different in sign, or they should always correspond in sign if both of them are non-zero. Okay.
I'm not sure I understand. Condition 2, does that mean that the Jacobian matrix is actually an injective function into the space of matrices, or do you mean that?
No, the linear map. Yeah, the matrix itself is invertible. Yep, that's all I mean. Yep. And then this part 3 just says, okay, now I take the determinant and look at what entries, what the entries in this determinant are, and they have this form. Okay. And what's perhaps a bit surprising is that a sufficient condition is if all of these terms are positive or all of the terms are negative. Okay. And in fact, that's equivalent in this setting when I'm restricted to interested in positive solutions only. Yeah. And then, so let me say that this, let me tell you part 4, and then let me remind you that this, the first 3 things were not our result, our contribution is the next piece. Okay, part 4. and this is our contribution. Is that the kernel of the matrix A? Okay, and another space, the image of B under a certain set. Okay, have no non-zero sign vector in common. Okay, so the kernel of A is fine. This is a subspace. Here I'm saying I take my subspace S and I look at, I take all of the sign vectors and then I look at the largest corresponding subset of Rn that has the same, that shares sign vectors with S. Okay. Yes.
So when you say R plus, you mean strictly positive or non-negative?
Strictly positive. Strictly positive.
B here is intersection with R greater than or equal to 0, or
So I'm saying greater than or equal to 0, but I'm only interested in the positive solutions. Yeah.
All these maps extend to the boundary they're given as.
at least
They're
exponential?
given
Yes.
by polynomials.
Yeah, of course. Yeah. But our result is about strictly positive ones. We have a result as well about boundary ones, but I'm not going to describe it. Okay, so again, I look at two sets, and I ask, are there any non-zero sign vectors in common between the two sets? Okay. And this is our contribution, that this condition about sign vectors is equivalent to these other three, which gives you a sufficient condition for having at most one positive real
So
solution.
the S there, that's the script S here?
Yeah, sorry. Script S.
Okay.
Yeah. The only reason I changed because I was afraid the flu example with the S would be confusing. So I mean script S all the way through.
Sigma is the sign vector?
Yeah, so sigma is a sign vector. So I take a look at all of the sign vectors, and then I today enlarge my set by all other vectors that share a sign vector with something else in that set.
So that's really saying about meeting certain orthants, or?
Yes, exactly. It's saying, does this set and does this set intersect the same orthants non-trivially? So outside of the zero vector.
Oh, so they meet different orthants. Is that right?
So it's asking, so if they intersected some orthant non-trivially, then this condition is violated. So you don't have injectivity. But if they do not, then our theorem says that it's equivalent to having this nice.
So if you list the orthants for one and the orthants for the other, they're different orthants. Is that what it says?
Right, exactly. So if I list the orthants for this or list the orthants for this, there should be none in common except for 0. Yep, exactly. Okay, good. And then let me say again that parts 1, 2, and the equivalents of parts 1, 2, and 3 were already 1, 2, and 3. Okay, we're done by Shiu and Feinberg. In 2005, and Liu and Wu in 2013. Okay. And then there was some intervening work that generalized to real to the setting of real exponent vectors and so on. Okay. But the point is everything works in this generality, so we might as well work in this setting as well. Okay, so. And let me just say in words, instead of drawing out some examples, that the nice application, even though this seems very contrived, right? This seems like this kind of condition would never hold. In fact, especially for very small networks, you can enumerate all of the small networks. Let's say you put some bound on how high you want the degrees of the polynomials to be. And it's actually the case for, let's say, up to 5 or 6 species. So not just susceptible, infected, and resilient. Maybe you'd also have some other classes of populations as well. That this injectivity criterion covers many of the cases when you don't have more than one steady state. So even though this seems sort of very contrived and surprising that this is useful at all, in fact, for very small networks, this is actually quite useful. Okay. So let's do part 3. Okay, so let's redo this theorem. Okay. So what I want to do now is to tell you another theorem, basically coming from this, that we can see if you look at these types of results from the point of view as you would of trying to solve systems of polynomials. Okay. So we write down the following theorem. So let A be an n by R matrix. Okay, and B is R by n. So let's assume that they're both full rank, and this is and n is less than or equal to R. Okay, so let n be less than or equal to R, and I want to consider matrices that are full rank. Full rank equal n. So let's consider for any y in Rn, I want to consider the following. So now I want to not have the funny kappas that are parameterizing my system, but now I want to parameterize by the solution set of a system. Okay, so I again want to let the A's be my coefficient matrices. So Aij, okay, times x1 to the bj1 dot 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 xn to the bjn. Okay, so now I'm writing down a system of polynomials again. J equals 1 to r, and I want the solution set to be some vector I. Okay, so this is for I equals 1 up to n. Okay, so I'm in a slightly different setting from what I was in the previous case. I'm just looking at a general system of polynomials, and I'm asking questions about the possible solution sets. Okay, so now let's write down the theorem we have here. Okay, so this part is not due to us, but rather to Creaciun, Garcia, Puente, and Frank. And it says the following. It says, again, let's look at these determinants, and we can use this as a criterion for when you can solve this system. Okay. So assume that for all j, so again, we're looking at subsets of size n, where n is the rank. Okay, these determinants determinant of b sub j n. Okay. Again, want to say they should all have the same sign, or they should be 0. Okay, so either is 0 or has the same sign as all other non-zero products. Okay, so I look at all these products. They should either all be strictly positive when they're 0 or strictly negative when they're non-zero. Okay. Then the system star, okay, then for all possible solutions, Rn, okay, star has at most one positive real solution x. Okay, let's say an Rn plus. Okay, so looking at all of these determinants will tell you, regardless of what my right-hand sides are, I will never have more than one positive real solution. And then a partial converse to this, then, which is due to Muller and Regensburger. Is that you could ask, well, okay, so now we have a condition for when you have at most one. When can I know for sure that there will be one? And under these assumptions, so assume, okay, that the row vectors of B lie in an open half space. And for all of these products here, okay, for all of these J, subsets of R, okay, the determinants have the same sign. Determinant of A sub n, comma J, and determinant of B sub J, comma n, okay, have the same sign. So now we're disallowing the cases where one of them is 0 and the other one is non-zero. Okay. In this setting, so then I can tell you exactly which of the y's actually have a unique solution. Okay, then star has a unique positive solution. Okay, if and only if y is in a certain polyhedral cone. Okay, and that's y is in. Let's say the relative interior, okay, of the cone generated by the columns of A. Okay, so I go back into the coefficient matrix A. Okay, I look at the corresponding columns and I look at the positive cone generated by this set, and those tell me exactly the y's that for which this system has exactly one positive real solution. And so let me just say out loud a few comments about this, and then I'll give you a few slides, and then we'll end. So this result, as I've explained, was not our result at all. Right? They were due to some earlier work. But our contribution is to recognize and to sort of highlight the fact that these results give you conditions for existence and uniqueness of at most one positive real solution. And in particular, if you think back to Descartes' rule of signs, right, it would be really nice, as many of you would hope, that there would be some nice generalization of Descartes' rule of signs for positive for the multivariate case. And this gives a tiny result in towards this direction in the sense that if you look at this system, right, and if you look at Descartes' rule of signs, it says look at the actual coefficients in your univariate polynomial, and you want to say look at the signs and then count the number of sign variations. Here, we say there is a recipe using the coefficients to tell you something about the number of positive solutions. It only gives you information up to 1, right? And this is very restricted, but nevertheless, most of the results from beginning with Khovansky and all of the theory of funomials that many of you in the audience have developed, typically, this is my understanding, only use information about the exponent vectors and not about the actual coefficients. And so here, in our case, we're highlighting the fact that here some information from the coefficients does give us some information about the number of solutions. Okay, so now I'm going to switch gears, give you 4 open questions, since I would like to highlight these applications and get some help from you in the future for proving more results in this form.
Can we get some lower bound as well by some index argument on the boundary? Should be able to integrate the map on the boundary.
Yes, you can. Actually, Khovansky has something about a lower bound like that. It's not published.
I don't know about this, but we do have results about the boundary, but quite restricted. Yeah.
But it's an index.
Index.
If I can go into these. Jack is warming up. Okay, very good. So now I'm just moving to the part where I just will tell you some 4 open questions that I hope that with your help we can solve. So another result about the positive steady states is on the other question, when do you know for sure you have at least one positive real solution? And so in some collaboration with Manoj Gopalakrishnan and Ezra Miller, we were able to prove by actually looking at the dynamics of the system that certain what we think of as inward pointing networks always have at least one positive real solution. Okay, so the picture is that something like the network on the right always has a positive real one, even though whereas ones on the left do not. So the difference between these 2 pictures is that what I do is I take the convex hull, or what you might think of as a Newton polytope, of the corresponding reaction network. Here it's a 2-dimensional system. We have C and D. Here we have a 2-dimensional system. It's A and B. Those are the 2 species. And I draw all of the reactions living inside of these lattices, and I ask for each of the faces of this Newton polytope, which is there some reaction that points from the face into the polytope. So here, if I look at all of the edges and vertices, there's always at least one reaction that points into the polytope, and it might pass through, which is okay, that's fine. Whereas in this case, in the network on the left, if I look at this edge here of this triangle, there's no reaction that starts on the edge and goes inward. So they're sort of, even though they're somewhat related, they're not the same. And we were able to prove something about the dynamics of systems like this. And in doing so, we could use something like a Brouwer fixed point argument to say, okay, so for sure inside of some large enough compact set, there for sure is going to be a unique, there's always going to be at least one positive solution. And so I want to wildly speculate that since I'm drawing Newton polytopes, maybe there's some connection to something like a Bernstein bound, right? If I gave you some polynomials, you would, many of you would do some kind of mixed volume computation and tell me how many complex solutions you would expect, right? And maybe there's some connection, even though I think it's sort of a crazy idea that there's some connection between the number of complex solutions and the number of positive real solutions. But nevertheless, maybe we should try and see what we get. Question 2. There are some conjectures about systems of this form. So let me just say it comes from biology, and it's a very common motif in signaling. And we want to know, can you please characterize for me the rate constants for which this has certain numbers of steady states? So one has 0, 1, 2, so on. So it's known by work of Li Ming Wang and Eduardo Sontag that you don't have any more than 2n minus 1. Okay, so this bound is known, but they conjecture that this bound of 2n minus 1 is actually not tight, and in fact should be n plus 1 and n, okay, for even depending on the parity of n.
What is this diagram?
Oh, so this diagram is like the fluid diagram I had here. So it's S0 plus E reacts to ES0 means you have someone of a person like S, a person like E, and they come together, and now there's a new person, ES0. Yeah. So I'm just drawing the came.
The fact that the points that they're linear, is that it?
Well, it's not linear because you have S0 plus E, and that's a degree 2, right? You have.
No, what I mean is it's a line.
Yeah, it's a line that's motif repeats.
The graph is a chain.
The graph is just a chain, and there's a family depending on n. So there's a chain here and a chain on the bottom as well. Yep. And so again, I'm asking the question, how many positive real solutions does the corresponding system of polynomials has, and how does it depend on these kappa? And the conjecture was known to be true for small n. Okay, that's the bounds come together. But recently, for every case except for when n is an even number greater than or equal to 6, the conjecture was disproven using sort of clever ways of moving these equations around. But it would be nice to answer the question for the case for n that's even. And maybe.
What sort of order of solutions do they have? Like, is
oh, it's instead of they were able to go one higher. I think n plus 2 and n plus 1. Yeah. Yeah, but not for anything for n greater than or equal to 6. Because the point is they could get n plus 1, but nothing better. Question 3. So a lot of times in biology, people do things that mathematicians would find appalling. So for example, this. So now these are different kinds of net reactions, but I could draw for you all of the corresponding reactions. Okay, but here these are the kinds of things that happen in biology. They wrote down the corresponding mass action ODEs, and then they said, okay, now I want to know how many positive real solutions there are. So what they did is they ran many, many simulations of these ODEs and then see where the solutions went to. But these are so. I hope that all of you are also appalled by this analysis of real solutions. But nevertheless, they can draw some nice pictures from biology saying, okay, maybe in this case you have 2 steady states and it corresponds to one case when your immune system reacted very violently to the disease, and this case where it reacted only a little bit, but it depends on the input, right? It depends sort of what kind of flu you got or something like that. So of course this is relevant for biology, but I think it would be nice if somebody could do maybe I would say a correct or maybe direct analysis of the steady states and understood the parameters better. Another approach, which I hinted at earlier, is, well, in this case you can use theorems about lifting steady states from small networks to large networks, which I want to say in question 4, and Alicia will say more later this afternoon. And maybe this would help us understand this immune system model. So this system is quite complicated, but it would be nice to understand which other subnetworks, which are the subgraphs of these graphs, that actually give rise to the steady states. And in particular, I want to highlight that people in biology care very much about this because, well, what is systems biology all about? It's about putting together a system's point of view from subsets. Okay, so you want to say if I know this component of the network has this property and this component has this, how can I put them together and understand the global picture? So in particular, that we have in joint work with Badal Joshi, we have results that say if your network has always inflows and outflows, so there's always people arriving at Simon's Institute and there's always people leaving Simon's Institute of every type SI and R, then we know a result of the form I was describing, that if some subnetwork has 2 or more steady states, then for sure the larger network will as well. But I think it's an open question. So this is not the only theorem of this form. There are several questions, there are several theorems of this form. But it's still open what other sets of pairs of networks can I lift from a small network to a large number to understand from a small system, if I have 3 or more steady states, 3 or more positive solutions, what can I say about the larger system? And so one thing you can do is then draw diagrams saying, okay, if I know this small network has 2 steady states, then for sure this one has 2 or more, and so on. Okay, so I'm going to just end with the summary. We gave some sign conditions for having at most one positive real solution for a whole family of whole parametrized family of polynomial equations, and they help us understand steady states. But what I hope to have convinced you in the last 4 or 5 slides is that there are many open and interesting questions for people who are applied like I am. And just to give an example to sort of highlight how subtle these questions can be, at least for me when I look at them, is if you look at this very simple network here, I have reversible reactions. So x1 plus x2, maybe they get together and they decide they want to leave the conference, and so they disappear. This is what I'm describing here. Okay, and so these sorts of pairs of people are always arriving and disappearing from the institute, and then I have no explanation for 2x. xn turns into x1. Maybe these are co-advisors and now they have a new student. I don't know. So if you look at this network for any n, you can actually show that for the case when n is even, there are no multiple steady states. So this system, if you write down the polynomials, never has more than one positive real solution. And in particular, you can use the sign conditions I described here to answer this question here. But then if n is odd, then it's actually the case that it does admit multiple steady states, so multiple positive real solutions. And for doing big results like this, you need to have results either that says, okay, if anytime you have a network of this form, you will always have multiple steady states, or you need this theory like I was describing of saying, if I know something about the small network, how can I go up to the large network? And so the result of Schlosser and Feinberg is the first type. It says if your network has this type, it has these conditions, and for sure you have multiple steady states. But it would be it would be nice to have a better theory of such system. Finally, there are 2 related talks that I wanted to highlight if you're interested in these types of ideas. And if you're even more interested, I'm looking to hire a postdoc. So if you or another person is interested in working with me, then please come talk to me later. And I'll end my talk there. Thank you.
Yeah, just a comment on question number 1. I think there was you were asking about some kind of analog and mixed volume for real roots or something?
Yes.
Yeah, so first steps were already taken. I mean, back in the 90s, I was working with Verreau and also later generalized by Sternfels. But there is this issue of creating some kind of mixed subdivision, counting alternating cells, and then there was a conjecture that would actually give you a correct bound for the number of roots. But that's the first step. I mean, that actually holds for certain polynomial systems in certain coefficient regions, but in complete generality, it's still a very, very hard question. But there is at least some kind of yoga for drawing little pictures and drawing little diagrams and getting something which works some of the time.
Oh, very good. So I should have known this.
This had to do with the systems that were extremely degenerated, close to being polyhedral. I guess that's the case, sort of in the limit of a degeneration. Good job.
In fact, I have a bone for this system.
So suppose you've got a system that satisfies the sufficient conditions for uniqueness of a positive solution. Okay? So yeah. Do the proof methods give you any hope that you can efficiently compute that unique solution, more so than you would by solving a general polynomial system? Is there something...
So the answer is generally yes, because a lot of times the systems, what happens is that either directly or under a change of variables, you have that the set of steady states is given by a binomial ideal. And so then you have a nice parametrization, and so then you have it on the nose.
Is that a general theorem that applies to all?
No.
So in other words, even if you satisfy, let's say, the sufficient conditions that come out of the what you called the I forgot what it was.
For injectivity.
Yeah, but both that and the existence of at least one. If you satisfy those, so you know you've got a unique solution, there's no better method in general than just applying an arbitrary polynomial solving thing to find it.
I don't think so. I don't know.
I mean, in some cases, this is like, at least Luis told me, in some cases you can use this method of statistics of interproportional scaling to invert these maps to find sort of a point here. Some of these can be viewed as there's a algebraic moment map and you're trying to find the inverse image of the pointer to that.
You can solve the
Bear probably knows that more.
Maybe I'll ask a different follow up on this. So one method would be to run the dynamics.
Yes.
Yeah, that's what I'm saying that they did. The biologists do this. Yeah. Oh yeah, I see. In that setting you would. Yes, I agree.
If you're using Brouwer's fixed point theorem, the dynamics could be it's going around in a circle and it's
So
never
that's
done.
what I'm asking. I mean, if you suppose you establish, have there been experiments about running the dynamics, how it compares to?
So that's what these biologists do, right? Going back to, yeah, that's what they do, is they just run the dynamics and see what you get. And then they say, oh, I ran this many simulations and I never got more than 4 steady states. So this is the answer.
There's one steady state, you have this Lyapunov function. How good is it? Is there?
In this, in the deficiency 0 setting, you have a Lyapunov function. It's a strict Lyapunov function, so it's very good.
It's a good one. So then you run the dynamics. And
Yeah, then you run the dynamics and the conjecture is that outside that it should be good to go. Yeah, generally it should be good to go.
I should remark, sort of advertising the type of questions you're asking. So this thing that I did with George and Luis, it was we had our interest in this was something from geometric modeling. So it's a completely different part of applied math.
I agree.
So these questions they're more interesting than just polynomials.
Yeah.
But they're probably most interesting for questions of poly. That's what the real money is.
in chemical networks, can you ever, the boundaries of the positive orthing, can the vector field ever be crossing the boundary?
In this setting, that doesn't cross the boundary. Yeah.
Is it tangent? Mostly it's pointing in from the boundary.
Mostly pointing in or along the boundary, depending on the situation, right? Because it could be that if there's no flu, then you stay along the no flu situation.
And then you probably have networks where there's always a little bit of contribution.
Yes.
Once you get inside, you probably can't. Can you tend to the boundary even?
Typically, it's conjecture that you know you don't tangent to the boundary. But when you go to this generality where you have real exponents, all kinds of crazy things happen. Yeah. But in straight up mass action, no. Generally. Yes.
So this polynomial map, which leads to injectivity, does monotonicity play any role in your arguments?
We use. I'm not sure if this is a question you're asking, but we definitely, since things are positive, we can take logs, right? And we use the monotonicity of the log, but I'm not sure if that's.
But we should discuss
There's
this.
a strict class of monotone systems for which there are several results proven. But not all of these are monotone.
Well, the reason I'm asking is because we have some definition of what should be considered as monotone maps, and I'm just wondering whether. Okay.
There's a whole theory of monotone. We can discuss afterwards. Yeah.
Any urgent question? Okay, so let's stop here.